In section 2.2, we're talking about the limit of a function. Now, having seen in the preceding section how limits arise when we want to find the tangent to a curve or the velocity of an object, we now turn our attention to limits in general and numerical and graphical methods for computing them. So let's investigate the behavior of the function f defined by this function x squared minus x plus 2 for values of x near 2. Now, if you look at the following tables, it gives values of f of x for values of x close to 2 but not equal to 2. Now, from these tables here, we can see that we're given a function that looks like a parabola, y equals x squared minus x plus 2. Now we can see that when x is close to 2 on either side of 2, the value of f of x is close to the number 4. So in fact, it appears that we can make the values of f of x as close as we like to 4 by taking x sufficiently close to 2. So if you look at your x values, we're getting closer and closer to 2, and then f of x is getting closer and closer to 4. Same thing on this side. As we're going from the right, 3 getting closer and closer to 2, again, f of x is getting closer and closer to 4. Now, we can express this by saying the limit of the function f of x equals x squared minus x plus 2 as x approaches 2 is equal to 4. So the notation would be as follows. We would say that the limit as x approaches 2 of the function x squared minus x plus 2 is equal to 4. So in general, we're going to use the following notation. So here's our first definition. We write the limit as x approaches a of the function is equal to L. If we can make the values of f of x arbitrarily close to L, or as close to L as we like, by taking x to be sufficiently close to a on either side of a, but the key word says, but not equal to a. Now another alternative notation for this is that the limit, again, as x approaches a of the function is equal to L, is another way of saying, as f of x approaches L as the value of x approaches a. Now going back to this statement here where it says, but not equal to a. I want to talk about that on this next slide. Now the phrase, but not equal to a in the definition of the limit. This means that in finding the limit of f of x as x approaches a, we never consider the fact that x is equal to a. In fact, we would say that f of x need not even be defined when x is equal to a. The only thing that matters is how f is defined near a. So when you look at these figures here, these graphs, these are the three functions, Now if you look at part C over here on this side, f of a, is a hole. It's an open circle, and it's not defined, And in part B, you can see that f of a does not even equal L because the point is closed here. But in each of these three cases, regardless of what happens at a, it is true that the limit as x approaches a of that function is going to equal L in all three cases. Okay, now here we want to guess a limit from numerical values. We want to guess the value of the limit as x approaches 1 of the function x minus 1 over x squared minus 1. Okay, so let's go ahead and then use our graphing calculator to determine some of these values. Okay, so what I'm going to do first here is I'm going to look at values of x that are less than or equal to 1. But we're going to start on the left side and approach the value of 1. So I'm going to go ahead and turn this on. Okay, I'm going to go ahead and put y equals. Now if you notice here, I've already put in the function x minus 1 over x squared minus 1. And then what I'm going to do is I'm going to create a table. So if I hit the second button and graph, and right above it says table, I'm going to hit second and then table. And so what I'm going to do is, because I already have the equation in for y1, whatever I choose for x is going to be the input, and it's automatically going to give us the output. So if we start at 0.5, it gives us 0.6667. Okay, let's go ahead and go to 0.9. Okay, and it gives us an output of 0.52632. Okay, if we put in 0.99, okay, it gives us 0.50251. Okay, if we put in 0.999, it gives us 0.50025. Okay, if we put in 0.9999, then it gives us 0.5003. Okay, so you can see here that as we start at 0.5 and we're getting closer and closer to 1, we can see here that it's getting closer and closer for the output to be 0.5. Okay, now these are all values that are less than 1. Okay, let's see what happens when it's greater than 1. So let's start at 1.5. Okay, if we start at 1.5, it gives us 0.4. Okay, if we go to 1.1, it gives us 0.476190. If we go to 1.01, it's given us 0.49751. If we go to 1.001, it gives us 0.49975. If we go to 1.0001, then you can see here, again, it's getting closer and closer to 0.5. So by using the values that are in this table, in both of these tables, okay, we can say that the limit of this function as x approaches 1 of x minus 1 over x squared minus 1 is going to equal 0.5. Okay. Now, another thing to look at here is that we can also make note of the following, and this is something that we're going to look later on. Okay, if you have x minus 1 over x squared minus 1, okay, the denominator of this rational function can be factored into x plus 1, x minus 1 using the difference of squares. Okay, and if we simplify the x minus 1, then what we end up with is 1 over x plus 1. Okay, now again, we're looking for the limit as x approaches 1. Now, if we plug in the value of 1 here, right, we actually get 1 over 1 plus 1, which becomes 1/2, which then equals 0.5. But again, that's something that we'll be looking at later on. Okay, now, in this first example, okay, it illustrated by the graph of f in this figure. Okay, now let's change f slightly by giving it the value 2 when x is equal to 1. Okay, so what's happening here is now we have a piecewise function. So the first piece, x minus 1 over x squared minus 1, if x does not equal 1, because it would make it undefined. And then you have the value of 2 if x is equal to 1. Okay, so if you look over here, okay, as the new function g still has the same limit as x approaches 1. So over here, okay, you can see here that as x approaches 1 on the right side, as it approaches 1 on the left side, again, the limit is still 0.5. Now over here, okay, if we look at the second piece, you can see here that we have this order pair here that represents 1, 2. Okay, and again, that's from the second piece of that function. So still, as x approaches from the right to 1 and x approaches from the left to 1, we still see that the limit is still 0.5. Okay, now in example number 2, we're going to estimate the value of the limit as t approaches 0 of square root of t squared plus 9 minus 3 over t squared. So I'm going to go ahead and put that in my calculator here. Okay, so I'm going to go ahead and put the function y equals. Now it's really important to make sure that you're using parentheses and grouping parentheses so you don't get any errors, because sometimes if you're getting errors, it's because the way you're entering the function into the y equals table. So here I'm putting in the function, okay, and I'm using x instead of t, okay, and I have parenthesis, square root of x squared plus 9, parenthesis minus 3, close a parenthesis, and then I have my division here, and I'm dividing it by x squared, okay. And so now when I want to go to the table, okay, I'm going to put in some values here. Now, if I'm putting in values of negative 0.1, if I'm putting values of negative 0.01, if I'm putting values of negative 0.001, so these are all negative. Now if I'm going to choose positive versions of those numbers, 0.1, 0.01, 0.001, and even 0.05, okay, and let's go ahead and put in another one here. Okay. Well, I guess the calculator's kind of slowing down here, but anyway, as you can notice here, okay, the outputs are all close to what? 0.1667 and so forth, right? So what it's saying here is that as t approaches 0, okay, the values of the function seem to approach 0.1666666 and so on. Okay, so what we can do is we can guess that the limit as t approaches 0 of the function, the square root of t squared plus 9 minus 3 over t squared, again, is going to be approaching 0.16666, which is the fraction 1 over 6. So that's where we're guessing. Okay, now if you notice, okay, these are the table of values that we can put into our calculator, and I'm putting them there just so that you can see what we just did in our calculator. Okay, so again, you can see here that it's approaching 0.16667. Okay, now in example 2, okay, what would have happened if we would have had taken even smaller values of t? So the table shown here shows the results from one calculator, okay? You can see that something strange seems to be happening. If we start going smaller by putting in a positive and negative value of 0.0005, we get 0.168. Now if we go even smaller, plus or minus 0.0001, you get 0.2000. If we put in even smaller, plus or minus 0.00005, we get 0.0000. Okay, so if you try these calculations on your own calculator, you might get different values, but eventually you will get the value of 0, like we did here, if you make t sufficiently small. Now, does this mean that the answer is really 0 instead of 1/6? Well, no. The value of the limit is 1/6, as you will show in the next section. Now, the problem is that the calculator gave false values, because the square root of t squared plus 9 is very close to 3 when t is small. So in fact, when t is sufficiently small, a calculator's value for the square root of t plus 9 is 3.000, to as many digits as a calculator is capable of carrying. So something similar happens when we try to graph that function, square root of t squared plus 9 minus 3 over t squared, on a graphing calculator or on a computer. So if we look at the first parts A and parts B, okay, it shows quite accurate graphs of the function f, okay? And then when we use the trace mode, okay, we can estimate that the limit is about 1/6. Now, but if we zoom in too much, meaning if we look at these graphs C and D, okay, then we get inaccurate graphs. And again, because of problems with subtraction. Okay, let's take a look at another example here. Okay, we want to be able to guess the value of the limit as x approaches 0 of the function sine of x over x. Okay, now again, what we want to do is we can put this function into our calculator we did in the previous example. Okay, now the function sine of x, right? So if we look at the function f of x, which is equal to the sine of x over x, is undefined where? Well, it's undefined when x is equal to 0. So that means that's the restriction. Okay, now using a calculator, and remember that if x is all real numbers, the sine of x means the sine of the angle whose radian measure is x. So when we construct the table of values correct to 8 decimal places, from the table here that you can see, okay, and the graph that you can see, okay, what's happening as we are approaching 0. So if we're approaching 0 from the right and approaching 0 from the left, okay, then what does that limit represent? Well, by looking at the graph, we can see that the limit as x approaches 0 of the function sine of x over x is equal to 1. Okay, likewise, if you look at the table, okay, as these values continue getting closer and closer to 0 on both the right and the negative side, again, it's getting closer and closer to 1. Okay, let's take a look at example number 4, which is a function with oscillating behavior. And again, we're going to investigate the limit as x approaches 0 of sine of pi over x. Now, again, we can say that when f of x is equal to the sine of pi over x, okay, it is undefined where x cannot equal 0. Now, we can evaluate the function for small values of x. Okay, so what happens? Okay, let's evaluate the function for when x is equal to 1. So if we take f of 1, then that is going to equal the sine of pi over 1 which is the sine of pi. And the sine of pi is equal to 0. If we take f of 1/2, so that would be the sine of pi divided by 1/2, which is the same thing as sine of 2 pi, which again is going to give you 0. If we take a look at f to the 1/3, so this would be sine of pi over 1/3, which again is the sine of 3 pi, which equals 0 again. If we take a look at f of 0.1, which is equal to the sine of pi over 0.1, well, that's the same thing as the sine of 10 pi, which again is equal to 0. And if we look at f of 0.01, that's also equal to the sine of pi over 0.01, which is equal to the sine of 100 pi. And again, that equals 0. Okay. Now, if we continued, we would see that regardless, you're still going to get 0. So by looking at these scenarios and guessing, we could be tempted to say that, okay, the limit as x approaches 0 of the function sine of pi over x is equal to 0. Okay? But in this case, our guess is actually wrong, because notice that although if we look at f of 1 over n, and we can call n whatever number that we want, right? That would equal to the sine of whatever n is times pi, and regardless of whatever n is, it's still going to give us 0 for any integer n. Okay? But it is also true it's also true that f of x, meaning the output, is equal to 1 for infinitely many values of x that approach 0. Okay, so when we look at this graph here, you can see that it's oscillating here. Okay, so as it's approaching here and here, you can see that it's approaching the value of 1. So the dashed lines near the y-axis here, okay, indicate that the values of sine of pi over x oscillate between -1 and 1 infinitely often as x approaches 0. So, since the values of f of x do not approach a fixed number as x approaches 0, then what we would say for this result is that it does not exist. So we would say that the limit as x approaches 0 of the function sine of pi over x does not exist. And then sometimes we just abbreviate that as DNE for does not exist. Okay, let's take a look at finding the limit as x approaches 0 of the function x cubed plus the cosine of 5x over 10,000. Now, I'm leaving these tables here, but I also want to use the calculator to find out what's happening. So let's go ahead and put this function into our graphing calculator. So we'll go to y equals, clear our graph, and we have parentheses x cubed plus the fraction cosine of 5x divided by 10,000. So let's go put in our table of values. So let's put in -0.1, -0.01, -0.001, 0.1, 0.01, and 0.001. Okay, so let's take a look at more of what's happening. So I'm going to take a picture of this. Okay, and I just want to investigate these values that we just created here. Okay, so when you take a look at -0.001, okay, the output here is 1 times e to the -4th, right? And then we also have 9.9 e to the -5th. Okay, so let's take a look at this number here. So keep in mind that we're talking about a scientific notation number, because this is the same thing as saying 9.9 times 10 to the -5. And so we're going to shift to the left the decimal places 5 times. So we should end up with 0.00099. Okay. Now, if we round this to the nearest decimal, so now if we round that 9 for this 0 then this is approximately 0.0001. Okay, now how do I write that as a fraction? Well, we know the 1 is in the 10,000th place. So this is actually 1 over 10,000. Okay. Now, by constructing this table and seeing what's happening with these numbers, okay, as it's getting closer and closer to 0, we can say that this limit as x approaches 0 of the function x cubed plus the cosine of 5x over 10,000 is equal to 0.0001, which actually ends up equaling 1 over 10,000. Okay. Now, these two examples, example 4, okay, and example 5, okay, they illustrate some of the pitfalls in guessing the value of a limit. So it's easy to guess the wrong value if we use inappropriate values of x, but it is difficult to know when to stop calculating values. And as the discussion after example 2 shows, sometimes calculators and computers give the wrong values. So when we talk about the next section, however, we will develop foolproof methods for calculating limits, because right now we're just guessing according to our table of values. Okay, let's take a look at example number 6. Okay, so a limit that does not exist. This is called the Heaviside function h and is defined by the following piecewise function. When h of t is equal to 0, that means that it's a horizontal line where t is less than 0. So that means it's approaching all the way to 0, but it doesn't include 0. Okay, and then another horizontal line, h of t is equal to 1, and it starts at when t is equal to 0 and then greater than 0. So again, here is a piecewise function. Okay, now this function is named after an electrical engineer called Oliver Heaviside and can be used to describe an electric current that is switched on at time t is equal to 0. And this is the graph that's shown. So what it's saying here is that as t approaches 0 from the left, then the function h of t approaches 0. Now, as t approaches 0 from the right, then the function is approaching the value of 1. So there is no single number that h of t approaches as t approaches 0. So therefore, we would say that it does not exist. Okay, so we would say that then the limit as t approaches 0 of the function h of t, okay, it does not exist. Okay, hence, which is what we're going to talk about when we talk about one-sided limits. So now we notice from this example that h of t approaches 0 as t approaches 0 from the left, and h of t approaches 1 as t approaches 0 from the right. Now we indicate this situation symbolically by writing the following. So the limit as t approaches 0 from the left, that minus represents that it's approaching 0 from the left, which is equal to 0. And the limit as t approaches 0, the plus meaning from the right, the function is approaching 1. So again, the symbol t is approaches 0 from the left indicates we consider only values of t that are less than 0. And likewise, t approaches 0 from the right indicates that we consider only values of t that are greater than 0. Okay, so this creates our new definition. Okay, our definition states the following. So we write that the limit as x approaches a from the left of f of x equals L, and we say that the left-hand limit of f of x as x approaches a, or the limit of f of x as x approaches a from the left, is equal to L if we can make the values of f of x arbitrarily close to L by taking x to be sufficiently close to a and x less than a. Now, if you notice that definition 2 differs from the definition 1 only that we require x to be less than a. Now, similarly, if we require that x be greater than a, then we would get the right-hand limit of f of x as x approaches a is equal to L. And then how would we write that? Well, we would write that down here like the following. We would say that the limit as x approaches a from the right of f of x is equal to L. So you can see what's happening with these two graphs. So again, as x approaches a of the function from the left is equal to L, and over here, f of x is approaching a from the right is equal to L. So the definition states the following. Now, the limit, this is an important definition. As x approaches a, the function is equal to L if and only if the limit as x approaches from the left of f of x is equal to L and the limit as x approaches a from the right of f of x equals L. So let's take a look at a similar example here. Okay, so looking at one-sided limits, we have example 7. So the graph of the function is shown here. So here's the graph of the function. Okay, and we're going to use it to state the values, if they exist, of the following function. So let's take a look at a. Okay, this states that what is the limit as x approaches 2 from the left of the function g of x. So here is the function g of x. Okay, and we're approaching the value of 2 from the left. So as we approach the value of 2 from the left, okay, this function is on the left-hand side, and as we approach it from the left, then the output up here is the value of 3, again, as we're approaching it from the left. So that equals 3. Okay, now, if we take a look at the second one, which is b, we want to figure out, okay, what is the limit as x approaches 2 from the right of that function? So as we're approaching 2 from the right, you see this function here, as this function approaches 2 from the right, well then the output here is what number? It's equal to 1. Okay, so now as the limit approaches x is approaching 2 of the function g of x. Now because these two limits do not equal the same number, then we would say that this limit does not exist from our previous definition. Okay, now let's take a look at part D. As the limit approaches 5, from the left. So here, as the limit of this function is approaching 5 from the left. So here's the function, starts here and it's approaching 5, then this number here is approaching what number? Well, the output here is 2. Now, this part E is asking us, okay, what happens when the limit of this function is approaching 5 from the right? Well, on the function, it's again approaching the value of what? 2. So in this scenario, when we're trying to find a limit as x approaches 5 now of that function, well, because it approaches 2 from the left of 5 and approaching 2 from the right of 5, then we would say that this limit actually approaches 2 because it satisfies that definition. Okay, and again, despite the fact, okay, despite the fact, regardless, that g of 5 is actually equal to 2. Remember, we go back to that one statement, that but that we said, it can equal a number, but it's actually approaching this value of 2. Okay, let's take a look at example number 8. Okay, we want to find the limit as x approaches 0 of 1 over x squared, and we want to see that if it exists. Okay, so this is our graph, and this is our table. Okay, so let's take a look at this graph. Now, as x becomes closer and closer to 0, okay, x squared becomes close to 0, and 1 over x squared becomes very large. So you can see here that it's getting large here. Okay, now over here, when you plug in those numbers, right, you can see that in a table of those functions, again, as you're getting closer and closer to 0, then these numbers are getting increasingly large as your outputs. Now, in fact, it appears from the graph of the function f of x is equal to 1 over x squared, shown in this figure, that the values of f of x can be made arbitrarily large, taking x close enough to 0. Thus, the values of f of x do not approach a number. So therefore, the limit does not exist. So we would say that the limit as x approaches 0 of this function, 1 over x squared, does not exist. Okay, let's take a look at example number 9. Okay, if we have the function f of x equals x squared minus x plus 2, how close to 2 does x have to be to ensure that the function f of x is within a distance of 0.1 of the number 4? Okay, so again, we're saying how close to 2 does x have to be to ensure that the function is within a distance of 0.1 of the number 4. So here is 2 on the x-axis. Okay, and here is the value of 4. So that is our order pair 2, 4. Okay, so we're looking at these values here. So if the distance from the function f of x to 4 is less than 0.01, then f of x lies between 3.9 and 4.1. So above 4 is the value of 4.1, and we create a horizontal line because that's within a distance of 0.1 above the value of 4. And then below 4, again, within a distance of 0.1, so 4 minus 0.1 gives you 3.9. So now what we've done is we created these two horizontal lines. Okay? And so what we're saying here is that we have this function, x squared minus x plus 2. And we're saying that it's going to be in between these two numbers, 3.9 and 4.1, because again, it's within a distance of the number 4. Now we need to determine the values of x such that the curve y equals x squared minus x plus 2 lies in between those two horizontal lines, y equals 3.9 and y equals 4.1. Now we graph the curve, okay, and lines near the point 2, 4 in that figure. And then with the cursor, we can estimate that the x-coordinate of the point of intersection of the line y equals 3.9 and the curve y equals x squared minus x plus 2 is about 1.966. Okay, and then similarly, the curve intersects the line of y equals 4.1 when x is approximately 2.003. So let's take a look at that on our graphing calculator. Okay, so we're going to put in the function x squared minus x plus 2. Okay, and then we're going to create our lines. So we got y is equal to 4.1. That's our horizontal line above that point. And then the horizontal line below that is 3.9. And then we also want to create a window so that we can see what's happening, because if we graph this right now, we don't get that clear of a picture. So now we got to use our windows and use our rectangles. Okay, so the values of x go from 1.8 to 2.2. And again, so that we can see that within our viewing rectangles. And then our y minimum, y max is 3.7 and then 4.3. So again, just enough for us to be able to see what's happening. Okay, so now we're going to go ahead and hit the trace button. Okay, so if we, if we go down here, and what happens at the value of 3.9, what is the value for x? Well, we can see that, and I'll go ahead and copy that here by using our trace button. And then let's do the other horizontal line and then go to the right here. And we can see that the point of intersection there is 2.032. Okay, so what we've determined here is that this is the value of x here, and this is the value of x here at those particular points. So we can say that 3.9, or the function x squared minus x plus 2, is in between these two numbers when the values of x are in between what two numbers? Well, we just determined that. One of them is 1.97 on the left, and the other one is 2.03. And so therefore, this function now is within the distance of 0.1 of 4 when x is within a distance of 0.03 of 2.